All right, so in our last lesson, I previewed that we were going to talk about the inverse of a matrix. Just like we have the inverse of a number, we can have the inverse of a matrix. So the answer I gave is the regular number, we have a reciprocal. So for example, if I have 5 times 5 inverse, 5 to the negative first power, that's the same thing as 5 times 1 over 5, which when I multiply those, I would get 1. So 1 represents our identity in the real numbers, just like we have an identity matrix in matrices. Okay, when we're dealing with square matrices, we have an identity matrix. Okay, so we're going to have a product of two matrices that is going to give us this identity. Okay, bear with me just a second. I'll try to get that focus a little better. So we're looking at the same idea. If I'm multiplying two matrices and I get the identity I, okay, we know this is I, right? It's probably I sub n, depending on what the dimensions of my A and my C are. A and C have to be the same dimension, otherwise I wouldn't be able to multiply them, okay? It's going to be the only way that would work out. And so if I have this property, that means that C here would be the inverse of the matrix A. Okay, and notice if I flip it around, I would get a similar result with C times A. That would mean that A is the inverse of the matrix C. Okay, and we use that same negative first power notation to represent the inverse of a matrix as we do for the inverse of a number. Okay, so that same negative first power produces what we are looking at there. Okay, so let's look at a quick example here. So say I have a matrix A that's going to be negative 5, 3, 7, and negative 4. So there's my matrix A. And then I'm going to have a matrix C here that's going to be 4, 3, 7, 5. Okay, we want to see what that multiplies to. Okay, so remember we go across the first row and down the first column. So negative 5 times 4 is negative 20, plus 3 times 7 is 21. So negative 20 plus 21 is 1. Okay, first row, second column, I have negative 15 and a positive 15. That makes 0. 7 times 4 is 28. 7 times negative 4 is negative 28. Add those together, you get 0. And then second row, second column, I have 21 minus 20, so that gives me 1. Okay, and this we recognize is the identity matrix in R2, right? That is a 2 by 2 identity, so that's I2. So what that means is my two matrices here, A and C, are inverses of one another. Okay, that should also mean that if I do C times A, I will get I2 as well. Okay, and remember, matrix multiplication in general is not a commutative operation. We can't in general switch A, C, and CA and get the same thing. But if they happen to be inverses of one another, then that will produce a matching result. Okay, so I would recommend for you, if you're struggling with matrix multiplication, switch those around, do C times A, you should get the same result. Okay, you get that same identity result. Okay, so this is helpful. This tells us that we know this particular matrix has an inverse, and we can write what that inverse is. We want to, of course, be a little more general than that, right? We're not always going to be given the matrix and its inverse. In many cases, right, we're going to be asked to find an inverse of a matrix. Okay, so let's start with some just broad notation so you can see where things are headed. So I've got a matrix A, B, C, D, just giving it some generic titles there. I'm going to have an matrix next to it that's going to be E, F, G, H. And I want it to be such that when I multiply these, I get the identity matrix in I2. Okay, so I know how to multiply these matrices. Now it's pretty abstract here, but I could still do the multiplication, right? I get A times E plus B times G. So A, E plus B, G. First row, second column, I get A times F plus B times H. So A, E plus B, H. Second row, first column, I get CE and DG. So CE plus DG. And second row, second column, I get CF plus DH. CF plus DH. Okay, and I know I want that to equal to the identity matrix because I want to determine if I can find some sort of general expression for finding the inverse. Okay, now as I'm looking at this, this looks difficult to possibly awful, terrible, heinous, whatever word you want to use there. Matching these up is going to be hard, right? I have 8 variables in here. I have 4 equations I could make, but getting those to line up is going to be tricky. So we want to come at it from a different approach, okay? But we know how to multiply matrices, so we feel like we should be able to line this up in a certain way. But just lining up these equations, I really don't have enough equations to deal with. So let's try to take it piece by piece here. I know that I want to take my starting matrix, A, B, C, D, and I want to get something that when I multiply, I get the identity, okay? Well, we know from linear systems that if I just reduce this to a column, okay? So instead of doing times a matrix here, let's just work on, can I find the first column of this matrix that will give me the first column of my identity over here, okay? So I can get things a little bit simpler. So I've got A, B, C, D. Okay, we're going to call this x1, x2, because that's what we're familiar with, right? We're setting up an ax equals b equation. Okay, my matrix equation, ax equals b, and then I'm going to use my first column of my identity. And then I can repeat this process for the second column, okay? All right, so let's dive into this here. I can set up an augmented matrix, A, B, C, D, augmented with 1, 0. Okay. Now, I know I want to get 1 here in the top left, so I'm going to divide everything by A. So I'm going to get 1 B over A and 1 over A, and my second row is not going to change. I don't know why I wrote theta and now 0. There we go. My second row is unchanged right now. Okay, so I took row 1, divided it by A, and replaced row 1. Okay, I know I want to get 0 below it, so I'm going to take negative C times row 1, add it to row 2, and replace row 2. Okay, now it starts to get a little ugly, but it's still something we can deal with. Okay, so I'm going to get 1 B over A and 1 over A in the top row. Nothing has changed in the top row. In the second row now, I'm going to have negative C plus C is 0. I have negative B over A plus D. So negative B over A plus D. Okay, augmented now. This is going to be negative 1 over A plus 0, so just negative 1 over A. Okay, so we're making progress here. We've got our 1, 0 like we like. We're starting to work our way through the algorithm. Okay, the next thing I'm going to do is I'm just going to go ahead and get a common denominator here, okay? Because I'm going to spare you all the gritty details of trying to work this inverse process out. But I want you to see where this terminology comes from. So this would have a common denominator of A. Okay, at this point, I get a common denominator of A. Oh, I forgot the negative C. Let me try that again. This is going to be negative BC. Remember, that got multiple. Sorry, I got ahead of myself. I'm going to get negative BC. I got the negative part, but I left off the C. That looks better. Sorry. I knew I was leaving off the C. I could see it was missing, and I tried to write it in the wrong place there for a second. Okay. So I have B over A there. So I've got negative. I'm going to get a common denominator of A. So it's negative BC plus DA divided by A, and negative 1 over A here. Now, the natural thing to do would be to scale this row here by multiplying it by A. So when I do that, I'm going to get 1. I'm going to actually scale the top row as well, just because it makes it easier. I'm going to get 1B1. Okay, bottom row is going to be 0, negative BC plus DA, and negative 1. Okay, so we've started to make some progress here. What I want you to notice is this negative BC over DA. Okay, when I go to get a 1 in this position, because that would be my next step, I would wind up dividing by this quantity, negative BC over DA. Okay, so there's a nice simple formula for a 2 by 2 matrix. Okay, for a 2 by 2 matrix, to find its inverse, we do the following. Okay, and this is theorem 4 in this section. Theorem 4 from chapter 2. So let me make sure I get a nice clear picture here, hopefully, a little clearer. Hey, if I have a matrix A that is A, B, C, D, I can define its inverse using the following formula. Right? It's 1 over AD minus BC. Okay, so notice that's that quantity here, right? I just wrote it in a different order. AD minus BC. Okay, we would wind up dividing by that in our next step. And we would work our way up to the next row. Okay, we would wind up putting, when we start subtracting out a B, we would divide, and then we'd wind up subtracting B. So that's where we're going to get that B from. Okay, and then what happens to the matrix part, as things get switched around a little bit, I'm going to have D negative C negative B A. Okay, so look at what has happened here. I took A and D and I switched their places. B and C stayed in the same place, but they both became negative. And notice here it is divided by this AD minus BC quantity. Now we could have kept going with this row reduction process, okay, and produced that result. The nitty-gritty details there are not really an important thing for our linear algebra class, but it is important that you see that this AD minus BC quantity is not just pulled out of the sky. It comes from doing those same row operations that we do before. Okay, so that is my inverse matrix setup here. All right, so that's how I find the inverse for a 2 by 2. Now notice this only gives me a 2 by 2. Okay, and we also want to notice one more thing. I have a division. And anytime I have a division, I have to account for the fact that I can't divide by 0. So AD minus BC cannot be 0, okay? So we say then as a property, A is invertible, okay? So we're defining another vocabulary word there. Invertible means that the matrix has an inverse. So A is invertible, parentheses has an inverse, and I will not write that parenthetical every time, but since it's the first time I'm writing it here, A is invertible if and only if, so IFF, right, is the abbreviation for if and only if, AD minus BC does not equal 0. Okay? And if that's the case, this is the inverse. Okay? Now, since this is an if and only if statement, we have a consequence here that A is not invertible if and only if AD minus BC is equal 0. Okay, and that is for a 2 by 2 matrix of that form. Okay, now we're going to expand this obviously to higher dimensions as we go in future sections and chapters, but for now, just looking at this 2 by 2 matrix setup here. Okay, we also give this quantity a name here, and chapter 3 deals with this quantity a lot more. We look at it in a lot more detail, but this is called the determinant. Okay, the determinant of A is equal to this quantity AD minus BC. Okay, and that gets abbreviated to DET. So DET of A is equal to AD minus BC. Okay. All right, so let's use our newfound methods to find an inverse. Okay, so I'm going to have a matrix A. My matrix A is going to be 3, 6, 2, and 1. 3, 6 first row, 2, 1 second row. So let's do AD minus BC. That's going to be 3 times 1. Okay, AD is the first diagonal. So we're going across the diagonal here, down the diagonal. So 3 times 1 minus 2 times 6. Now you do have to be careful with the sign, S-I-G-N, positive or negative. Make sure you're careful with that when you add this up. So this is 3 minus 12. This is a negative 9. Okay. So my inverse matrix then, remember it is 1 over this determinant. So look back at your formula. It's 1 over the determinant. Okay. So I'm going to have negative 1 over 9 in the front of my matrix. Okay. I take the numbers on the diagonal here, A and D, and I switch places. So that's going to be 1 and 3. The other numbers, the 2 and the 6 here, the numbers on the off diagonal, stay where they are, but they become negative. So negative 2 and -6. Okay, and then I can go ahead and simplify this if I need to. This is fine most of the time. Pay attention to the way my math lab asks for the answers, whether it asks for a single matrix or things like that. For me, on a quiz or a test, this would be a perfectly fine answer if I was asking for that inverse. But sometimes we might need to simplify that. We can multiply this just like any other scalar onto the inside. So I'm going to get -1/9. I'm going to get a positive 6/9. I'm just going to write it unsimplified for the moment, and then I'll simplify in a second. Negative times negative down here is just going to be a positive 2/9, and then a -3/9. Okay, and then of course we could simplify that further. So I'd have -1/9 is fine. This would be 2/3 when I have 6/9, 2/9, and 1/3 for 3/9. Let me make sure I get my negative signs in there. That's -1/9 and -1/3. There we go. And now I've got my inverse without too much difficulty, too much consternation there. Okay, nothing too difficult for us to deal with. Okay, so let's do one more of this type. Okay, so I have my matrix here: 2, 1, -1, and 3. Okay, so let's find the determinant here first. This is going to be 2 times 3 minus -1 times 1. So here's one where, like I was saying, be careful with your sign, your positive and negative signs. I've got negative and negative here is going to be plus. So this is going to be 6 plus 1. It's going to be 7. So my inverse is going to be 1/7. Remember, it's 1 divided by the determinant. Okay, you take the numbers on the main diagonal, in this case the 2 and the 3, and they switch places. And the numbers on the off diagonal become negative, but stay where they are. So negative and -1 is actually a +1, and then -1 in the upper right. And again, we could write this as a matrix without a scalar in front. We would have 3/7, -1/7, +1/7, and a +2/7. Looks great. Okay, so a pretty straightforward process for finding that determinant. Okay, find that determinant, we use that to find our inverse. Okay, now we know we can multiply matrices, so let's make some observations here. If I have A times A inverse, I know that gives me the identity. Okay, all right, well, I also have a matrix equation that I know about. If I have AX is equal to B, our old familiar matrix equation, well, let's do some work with the inverse. Let's first also remember I can switch the order. I can do A inverse A. Remember that when you multiply a matrix, it matters whether or not you do it on the left or on the right. Okay? Remember, matrix multiplication in general is not commutative. So as I'm looking here, most of the time when I'm working these equations, I'm trying to find x, right? Where x is a vector that we're familiar with. Looks like x1, x2, maybe x3. You know, we don't know exactly how far down that continues, depending on the system. But I'm trying to find x. So let's get x by itself. Good old faithful algebra 1 class, right, from high school. Get x by itself. Isolate x. So I'm going to multiply on the left by A inverse. But whatever I do to one side, I have to do to the other side of the equal sign. So I multiplied them both by A inverse. But I know that A inverse A is the identity. I also know that matrix multiplication is associative. So I can mix up the order. I can do AX first and then do A inverse, and do A inverse A first. I know this is the identity. So this is I times X. That gets me A inverse B on the left, okay? And I maybe wrote down one extra step there by going and putting that I. Anything times the identity is just itself. So this tells me that X is equal to A inverse B. So I can use this to solve linear systems. Okay, we're always kind of looking for a better mousetrap in this class. We're finding better ways to do things, different ways, so that we have a whole bunch of tools available at our disposal. Okay, so let's look at a system here. I have a system that's 8x1 minus 7x2 is equal to 2. And the negative 4x1 plus 4x2 is equal to 5. Okay? So as I look at this system is a matrix 8, negative 7, negative 4, 4, coefficient matrix, times a unknown vector x, in this case x1, x2, is equal to a vector b, 2, 5. I can write my system in that form. We talked about that in chapter 1, going between the system notation. Okay, this is a system of equations. Turn that into a matrix equation. We could turn it into a vector equation if you prefer, right? We'd have this first column times x1, the second column times x2, and our result would still be b. So we have a few choices there. And we talked about doing row operations for that. Okay, and we certainly could do row operations. Get some big numbers. Maybe that's a little arduous, but I can find A inverse here. So this is A. So we're going to find A inverse. So first, remember this is the determinant, 1 over the determinant. So 8 times 4 is 32. Minus negative 7 times negative 4 is 28. So this is 1 over 4. 32 minus 28 is 4. We multiply that by, we switch the numbers on the diagonal. So 4 and 8 switch places. The other numbers stay where they are, but they become positive. Okay? And now I can simplify this matrix a little further as well. I multiply that by 4. So 4 divided by 4 is 1. So that's the first column. Second column is going to be 7 over 4, and then 8 divided by 4 is 2. So we have my inverse matrix here. So I can use that inverse matrix with my newfound equation here. I can simply do x equals to A inverse times B. So A inverse I just found, 1, 7/4, 1, 2. And B is what I'm looking for over here, 2, 5. Okay, and I can just do that with multiplication. I don't need any complicated row operations now. I can just multiply. And multiplying is a lot more straightforward a lot of times, right? So 1 times 2 is 2, plus 35 over 4. Okay, so 1 times 2 is 2. That's 8 over 4, plus 35 over 4. That's 43 over 4. Okay. Second row, 2 times 1 is 2. 2 times 5 is 10. Add those together, and I get 12. Okay. You might see 34 over 4. You might make that a decimal. So we'll say 10.75 over 12. That's a fine answer as well. Either of those representations are good here. So we can use an inverse to determine the value of a linear system. Okay. And so we're going to codify that as theorem 5 here for section 2.2. Theorem 5 says if A is an M by N matrix, I'm sorry, not M by N, I wrote that wrong, N by N matrix, then for each B, so each vector B that's an element of Rn, the equation AX equals B has a unique solution X equals A inverse B, provided A inverse exists. Okay, so if A inverse doesn't exist, if the matrix is not invertible, then you don't have this property. This only works if you have that A inverse exists. Okay. Now, what else do we know about this type of matrix equation? If I have AX equals B, that means I have a matrix A times some vector X, we'll represent in our usual way, times is equal to some B vector as a solution here. Okay. And I know, so we'll call this A, that I can find this by, instead of doing this method, I can find this solution by taking A and augmenting it with the vector B. Okay, so I take A, augment it with the vector B. And I row reduce this. Okay, and if I have a unique solution, then I get the vectors X here with the identity matrix on this side. Okay, so that is my identity matrix. And I also know from chapter 1, specifically section 1.5, that if this is the case, then the vectors are linearly independent. And I know then if the vectors are linearly independent, then that would mean since I have n copies of them, this is I sub n, then these vectors span the entire space of Rn. Right, so given these vectors span the entire space here, we can use that to make some additional observations when we are working. So we get some additional properties here as a result, okay? So what that says is, and I'm going to come back to theorem 6, okay? I'm going to go in a slightly different order than the book does. I'm going to go ahead and jump to theorem 7 here. I will talk about theorem 6. We will do it, but I like this segue a little better than the way the book segues it. So an n by n matrix A is invertible if and only if, remember IFF is if and only if, A is row equivalent, so that means we can do row operations to get it there, to the matrix IN, to the identity matrix, okay? So an n by n matrix A is invertible if and only if A is row equivalent to the identity matrix, okay? This is not part of theorem 7 now, but by default that also means that the columns of A are linearly independent. Okay, again, not part of theorem 7, just an observation we can make because I now know it's row equivalent to the identity. So I have a pivot in every row and a pivot in every column. And then also from the same area, I know that the columns of A span all of Rn. So I can make any linear combination in that space, okay? Now, when I'm doing those row operations, let's think about what's happening here. So if I take a matrix A, I'm going to take a matrix A. This matrix is 1, 0, -2, -3, 1, 4, 2, -3, 4. Okay, now as I look at this matrix A, I'm not sure that it's linearly independent, but I feel like it probably is. There's no multiples here. Nothing adds up super easily. Okay, but we can always check, punch it in your calculator. I will tell you that this matrix is linearly independent. These columns are linearly independent. We do get the identity matrix, okay? Now, we also know that if I do these operations in the other order, if I start here and just reverse all the ones I do, I get back to the matrix A, okay? Well, I know A has an inverse, okay? It's independent, A has an inverse, okay? So A inverse exists, okay? So there is an A inverse. I don't know what it is right now. And I know that I can row reduce it. And since A inverse has an inverse, in this case A, right? Remember, we can go either direction here on the inverse. If I row reduce it, I'm going to get the identity matrix. Okay, I'm going to get the identity matrix. And then I can reverse those row operations and get back to my inverse. So what I can do is I can do both of these operations at the same time. I can take my matrix A and augment it with the identity. In this case, it would be I3. And I can simply row reduce both of them at the same time using the same operations. And when I do so, I'll get I3 on the left and I'll get A inverse on the right. Okay, so this is a inverse finding algorithm for us that we now have. Okay, so let's look at it with this matrix A that I just wrote down. I'll write it down again for you here on the next page. So my matrix A, again, is 1, 0, negative 2, negative 3, 1, 4, 2, negative 3, 4. Okay, and we said to find A inverse, let me not say A equals here, because I want to go ahead and augment it. To find A inverse, I'm going to augment it with the identity matrix. Okay, so this is A on the left and I3 on the right. Okay, we're going to start row reducing this. So I'm going to do 3 copies of row 1, add that to row 2. It's going to replace row 2. I'm going to do negative 2 copies of row 1, add that to row 3. It's going to replace row 3. Okay, so row 1 doesn't change. It's 1, 0, negative 2, 1, 0, 0. Unchanged row 1. I go to row 2 now. Negative 3 and 3 is going to make 0. Okay, 3 times 0 is 0, plus 1 is still 1. So that looks good. That's going to make it easier to keep reducing. Okay, then we go to the next spot. I've got 3 times negative 2 is a negative 6, plus 4 is a negative 2. Okay, remember I multiplied this row by 3 also. Okay, so 3 times 1 is 3, plus 0 is 3. Okay, it's augmented, remember, just keep things separate. Keeping going, 0 times 3 is 0, plus 1 is 1, and 0 plus 0 is 0. Okay, third row now, I've got negative 2 plus 2 makes 0. 0 times negative 2 is still 0, plus negative 3 is negative 3. Negative 2 times negative 2 is a positive 4, and 4 plus 4 is a positive 8. Okay, then here I've got negative 2 times 1 is a negative 2, plus 0 is negative 2. 0 plus 0 is 0. 0 plus 1 is going to be 1. Okay, that's good. Now remember, so there's my first pivot, there's my second pivot. Now I go below my second pivot. So I need 3 copies of row 2 to be added to row 3 and replace row 3. So row 1 is unchanged. Row 2 is unchanged. Okay, remember it's augmented, so I'm going to keep that dashed line to help remind me. Multiplying this by 3, so 3 and negative 3 makes 0. 0 and 0 is 0. 3 times a negative 2 is a negative 6, plus 8 is 2. Negative 6 plus 8 is 2. Okay, then we go across here. I've got 3 times 3 is 9. 3 times 3 is 9, minus 2 is a positive 7. 3 times 1 is 3, plus 0 is a positive 3. 3 times 0 is 0, plus 1 is a positive 1. Okay, so that's progress. Now I'm going to work up from the 2, remember? So I'm going to take row 3, add it to row 2, and replace row 2. And then I'm also going to do the same thing for row 1. Okay, I didn't scale this here because this 2 with those negative 2s will make for some easier row operations. Okay, so row 3 is the row that doesn't change now. For now, we can fix it in a second. So row 3 doesn't change for now. So I'm going to go to row 2. So 0 plus 0 is 0. 0 plus 1 is 1. 2 and negative 2 makes 0. 7 and 3 makes 10. 3 and 1 makes 4. And 1 and 0 makes 1. Okay, then do the same thing for row 1. So 0 and 1 is 1. 0 and 0 is 0. 2 and negative 2 makes 0. 7 and 1 is 8. 3 and 0 is 3. 1 and 0 is 1. Okay, so the only thing left to do is I need to scale this row. I need to divide it by 2. I'm just going to do it right here. I'm going to make that 1. This is going to be 7 halves, 3 halves, and 1 half. So I can then say that my matrix A inverse is equal to 8, 3, 1, 10, 4, 1, 7 over 2, 3 over 2, 1 over 2. And that gives me my inverse. So I have an algorithm now that I can use for larger systems than just a 2 by 2. Okay. Now we want to also make an observation here that I could do this just one column at a time. Maybe I only needed column 3 of A inverse. Well, I could take A and augment it with the appropriate identity column. Okay, so if I needed column 2, I would have 0, 1, 0. If I needed column 1, and when I row reduce that, I'm going to get the identity, of course, and I'll get the third column here because that's what I started out with way up here was 0, 0, 1. And I would do all these row operations in exactly the same order, and I would wind up with 1, 1, and 1 half. So you can do just a single column of the matrix at a time if that is what's needed, or maybe that's, you didn't need the whole inverse. You only needed to know a small piece of it. So you can use that to find a single column, okay? So you take A and however many columns of the inverse you need on the augmented side, okay? Now I promised I would go back to theorem 6, and I'm gonna do that here. And we'll talk about some algebraic properties that go along with this, okay? So theorem 6 says if A is invertible, then A inverse is invertible. We actually already know that. That's something we've discussed to this point. We've used that together. Okay? And the new part of this here is that if I take the inverse of the inverse, I just get back where I started. So A inverse is just A. Okay, so that is part 1. Okay, part 2 is that if A and B are n by n invertible matrices, then AB, their product, is invertible. And AB inverse, much like transpose from the last section, switches the order. It's B inverse, A inverse. Okay, it switches it around. Okay, and then theorem 3 here, if A is invertible, then so is, enough room there, I'll write it there, A transpose. Okay, we just talked about transpose last section. That's switching the rows and columns. It makes sense if the you have that dependence relationship. You don't have that dependence relationship. Just switching those around, you're still going to have that independent property. So A inverse is, and we get some more algebra here, that A inverse transpose is equal to A transpose inverse. So we can actually flop those inverse and transpose around in the algebra, okay? Now, there's lots of little sort of algebra exercises you can do here with these. So, for example, if I know that AD is equal to the identity, well, I can prove that D is A inverse. So if I'm trying to prove, maybe I'm trying to get it by itself. Well, I'm going to multiply both sides by A inverse. Okay, I multiplied it on the left so that A inverse and A would be next to each other. If I put it on the right, then I would have that D in the middle, which would be a problem. So A inverse A we know is the identity. A inverse times the identity we know is just A inverse, because anything times the identity is itself. And then we can use the same thing on the ID side. So D is equal to A inverse. There's lots of little sort of short algebra type almost proof exercises you can do using these properties, okay? But remember, you have to take care that you multiply your matrix on the correct side. If you don't multiply on the correct side, that can lead you astray, okay? So let me take a moment here. I want to look at one problem from the homework to kind of get you started. You can see what I'm talking about with these algebra situations. Okay, so I'm going to share my screen here from this homework problem. Okay, so we can take a look at this homework problem here. So it gives us this setup. AB is equal to AC, where B and C are N by P matrices, and A is invertible. Show that B equals C. Okay, is this true in general and A is not invertible? Okay, so I have this property here that A is invertible. Notice that's given. A is invertible. Okay, so since A is invertible, the matrix A inverse is going to exist. Okay, and then when I go to write this equation, I'm going to use that same property I just used here, where I'm trying to get B and C together. I'm trying to get B equals C. So I want to put this A inverse on the left. So I get A inverse AB, and then whatever I do on one side of the equal sign, I have to do on the other side of the equal sign. Okay, and that gets me an equation there, and then I can continue from there using the various properties that we've talked about. If I take the inverse times itself, I get the identity. Okay, so I've done a huge chunk of this problem for you to set it up for you here on number 10. So that's your reward for watching all the way to the end of the video as well. Okay, that's number 10 in the homework number 12, section 2.2. Okay, and so there's lots of little jumping off, little algebra exercises you can do using those properties. Okay, make sure you keep the multiplication on the correct side, so forth. Okay. So lastly here, remember you have all these different setups with the span. Okay. Linear independence is tied to invertibility. Okay. And if you have an invertible matrix, then you get the entire span. So when we get to 2.3, we're going to actually write down a list of these theorems that go together because they are all equivalent to one another. Right? We've been talking all this way about how one thing leads to another, and we just rename it. So we have all these theorems that tack on one after another that we get all these properties together. Okay. So again, if you have any questions, please contact me. Please let me know how I can be of assistance. Send me an email. Come by the office hours, and I would be happy to assist you. We're coming up pretty quickly on the second check for understanding, and then the one of the exams comes up at the end of chapter 2. Okay, it's possible I've reused this video from a previous semester and not the first one. In general, there's typically an exam there at the end of chapter 2. So go back, check those course checklists, check your course schedule, make sure you see where those exams are, make sure you're prepared and doing everything you need to do. Again, please be in touch if I can help. And I'll see you when we talk about the invertible matrix theorem in section 2.3. See you then.